Hey guys, let's discuss new topic from system design, which is called rate limiter. So we are designing here rate limiter. I've already created one rate limiter video where I have explained the theory part, and here we will design the rate limiter. Okay, so I assure you the session will be very interesting. Just be with me till the end, and because here we will be discussing AI. Okay, LLD low level design with AI, without AI. So let's start. So the problem statement is you need to design rate limiter, okay, which will restrict the request. So which request? Let's say you have defined a request like 100 requests per minute per user, means one user can send only till 100 requests at max, okay, per minute, and if it is more than that, then we will block him for particular time, or we will send the and also we will send the message that please try after 30 seconds or 1 minute or something like that. Okay, so but the requirement is it should work with the distributed microservices architecture. Okay, and then definitely low latency and high scalability, these are the common things, right? Low latency means user is sending request, and then the time he will get the response should be low, so latency should be low. Okay, how late the response is coming, that should be low. And then high scalability, so tomorrow if we add the number of servers, then also we should be able to do that. So now let's talk about functional requirement, and here we will be talking about 8 to 10 functional requirements. Okay, so first one is limit request. So request on the basis of user ID, okay, IP address of the system, then API key and services. Okay, so you can limit with various parameters. So we will concentrate on these ports. Now, for example, 100 requests per minute per user. That is the example. Now, second is multiple rate limit rules. So the rate limit rules should be different for each APIs. For example, if it is a login API, then 5 requests per minute is sufficient, right? It means user can try to log in, number of attempts is equivalent to 5 per minute, right? And then if it is search, so he can search lots of data, right? So for that I will change the rate limit to 100 requests per minute. Okay, and for payment API, 10 requests per minute, because for payment that much will be sufficient. So now third one is configuration limit, configurable limit. So admin, if wanted to change this configuration, these numbers, okay, he should do that without restarting the server. So it should be configurable, dynamic config without restart. So now for example, if user 123, it is we are limiting by user ID, limit change from 100 to 200. Okay, now the fourth one is distributed support. So what is distributed support? Must work across multiple servers, and same user hitting different instances is still limited. So like for example, I have multiple servers. Okay, maybe I have a copy of a server, load balancing, then it should work, okay, across these multiple server configurations. Means if user has a request for the server 1, okay, 2 times, and server 2 again 2 times, so overall it should calculate it as 4 requests till now he has hit on the server. Okay, so it should work across multiple servers. Now same user hitting different instances, still limited. Okay, now return proper response. So here we will return 429, which is too many requests. Okay, this is the HTTP code, and then include retry time also, that hit after 30 seconds, something like that. Now support multiple algorithms. So we have seen 6 algorithms of rate limiting. Okay, I'll not go in detail those algorithms here, but for example, token bucket, sliding window, fixed window. So when we will see the low level design, that time we will create a class for each algorithm. So we will use the strategy design pattern here. Okay, and whatever is required, you just implement object of that class. Now whitelisting and blacklisting. What is whitelisting? Blacklisting means allow trusted clients and block abusive clients. Okay, so you just add those detail into this tables. Burst handling, so allow short burst, limit is 100 per minute, so burst 20 is allowed, means I'm saying that user can send 100 requests per minute, okay, but in 1 second. So let's 0 to 1. So here, what if here itself we like last a second, okay, when 1 minute is just about to complete, that time he will send the 100 request, okay. So that should not happen, because that is the spike in the traffic, right? So for that he should burst should be 20 is okay, okay. So per tenant per user limit. Now what is per tenant per user? See, per user means individual users, okay, and per tenant means organization, okay, organizations, companies. So they will come in the tenant category. So for example, if user is free, okay, so we will give him 100 requests per minute. If he is premium user, then we will change the number of requests, okay, 1000 requests per minute. So these all are the functional requirement. We need to do these things. Now let's talk about non-functional requirement, and here the non-functional requirement, again we will discuss 8 to 10 requirements, okay. So these are the common things. Low latency, okay, latency should be less than 5 milliseconds. High availability, okay, if you need to add more servers, then rate limiter failure should not block entire system, okay. If anything is failed, then for example we will use here Redis server, okay, for the storing the value. If that gets failed, okay, you should have the copy of Redis server in a cluster, so that a request will go there, and your entire system will not crash, okay. So fallback strategy is required. So here fallback strategy was, we have created the copy of the server. Now scalability, so must handle millions of requests per second, okay, and horizontal scalable. So horizontally you can add multiple servers here. Fourth one is consistency. So consistency would be two approaches we will use here. One is a strong consistency, second is eventual consistency, okay. So strong consistency is accurate limit, and eventual consistency is faster. So let's before going further, okay, before going further non-functional requirements, let's discuss this strong consistency and eventual consistency model here, okay, in rate limiter. So what is a strong consistency? Let's say if limit is 100 requests per minute, okay, and user is sending so means first 101 request, the last request will come, okay. So that we will block, okay. We will be very strict here that we will not even entertain any one request, okay, even the +1 request. So here how we will implement it? So using centralized restore, which is called Redis, okay, but with Redis you use the atomic operations, okay. Why atomic operations? If two requests are hitting at the same time the Redis server, okay, the operation should be atomic. Then distributed logging you can use, synchronous updates you can use. So for example, if you have 3 servers A, B and C, and count A can see the count, okay, users send 100 requests from 3 different servers. So A also should see 100 count, B also should see 100, and C should also see the 100, okay. Then 101 request come, so you just directly block that. So that is the strong consistency, okay. Now what is the cons here? High latency, okay, because this is a strong consistency, so he has to sync all the servers and then need to give the final result, okay. So bottleneck, what is bottleneck here? Single source of truth, one server only. Less scalable, okay. So use cases where you will use this strong consistency, payment API, okay. You know that payment is critical, and we always use the trade-off consistency there instead of availability, right? Then login attempts, so because it is related to security, so there also we need to have a strong consistency. Then OTP system also strong consistency. Now let's see eventual consistency. Eventual consistency means you have multiple servers and data will get reflect in another server, okay. It will get reflect, but after some time. Eventually it will get reflect, but it will take some time. So it means that when 100 request is completed and 101 request will come, okay, we will allow that request, because currently your system is not consistent, the other system is not consistent, okay. So that's why some extra request may pass, fine. Now how it's implemented? So local counter per server, okay. In each server you just have the local counter. In strong consistency, in centralized global Redis server, you were having one counter variable, and all the servers were synchronizing the value from there. Okay, but here you will have a local counter variable, okay, per server, and we will sync it asynchronously. Means using Kafka or background job, it will get sync, but asynchronously. It should take some time also. So sharded counters also. Means sharded counters means in multiple servers you will have their own counters. So now let's see, if limit is 100 requests per minute, okay, and so A will see 90, B will see 85, C will see 88, okay, all the servers are seeing different limits. So users send requests to different servers, total might become 110 or 120 before sync. So means you have sent 10 or 20 requests extra, right? Limit was 100. So overshoot allowed here. Okay, now what is the pros? So this is very fast, low latency, right? This is highly scalable and no central bottleneck here. Now what is the cons here? So 100% accurate, it is not 100% accurate. Okay, we have seen that every server will see different count, and can be abused slightly, and inconsistent user experience. What is the use cases here? So public APIs like social media. Okay, so in social media you need to see the number of likes on a post. Okay, so user can see the outdated value also there, but there he should see the post. That is the important. So availability important there instead of consistency. Now analytics events or non-critical throttling. Now fault tolerance, let's talk about fault tolerance. Okay, this comes in a non-functional requirement, so your system should have this fault tolerance. Okay, so if let's say if your Redis server failed, okay, or your network partition, means you have servers here and the network connection break. Okay, so there is some partition in a network, right? So that is network partition, so that also should handle properly. And instance crash, any server gets crashed, then in that case also system should degrade gracefully. Okay, now throughput, so should handle 100k to 1 million requests per second. Accuracy, so avoid over throttling and under throttling. What is over and under? So means blocking request even if user is within limit, and allowing requests beyond the limit. So how it is possible? So let's see if the server if the clock they are using is not in sync. Okay, server clock is different, client clock is different, so always use the server side clock. And then config propagation, so config changes should propagate quickly, like in less than 10 seconds. Observability, so what all thing you will observe here. Okay, so throttle request, how many requests came. Okay, throttle means how many requests you are processing. Then allowed request per user limit and errors. Now monitoring tools, what you will use here, Prometheus and Grafana you can use. Okay, now security, so prevent bypass. Okay, that logic should not get bypassed, and avoid header spoofing. What is the header spoofing? So a client fakes or manipulate HTTP headers to prevent to be someone else. Means the client is same, but he is changing the header, HTTP header, so that the system will think that this request is coming from different system. Okay, so this thing also we need to take care. Then protect internal APIs. Now rate limiter without AI. Okay, first we will discuss about traditional way, and then we will add AI functionality here, so that it will be easier us to understand how it was before AI, and how what things has been changed. See, all the videos you have on the YouTube right now on system design is the traditional way. Okay, so it is hardly very few videos maybe they have created on the latest system design topic, because currently I am creating system design videos. That's why definitely I will add this functionality in my videos, right? So let's add that and let's check that. Okay, so without AI, traditional way, if you check, so algorithm, see, you can use token bucket, leaky bucket, fixed size bucket, sliding window. Okay, sliding window counter. So these all things. So this is the diagram. So client will send the request, load balancer will so before API gateway we have a load balancer, and then it will rate limiter service, so it will check the request. Okay, how many request has came from this client, and then it will store in a Redis counter store. Okay, now data store, so use fast in memory store like Redis or memcached. So we use this to cache here, this in memory stores here. Okay, So what will be the key format? We know that Redis is key value pair kind of storage, right? So rate limit, and then rate limit will be user 123 and value will be number of counts, and expiry will be 60 seconds. Okay, so in 60 seconds this will get expired. Now what is the example? So for example, if I am saying 5 requests per minute we are allowing. Okay, so at 10 o'clock and first second, so first second, if first request is coming, okay, so per minute means 60 seconds. So first second, if request is coming, we are allowing it, because we can allow 5 requests. Fifth second allow, 10th allow, 20 allow, 30 allow. Okay, still it is 5. Then at 40th second, when the request came, we are rejecting it. Okay, so that is fixed window. Now what is token bucket? So if you have token okay, so next one is token bucket. So token bucket, you will have one bucket, and let's say its capacity is 100. Okay, and refill rate for to refill that bucket is 10 tokens per second. So in that case, you will check when the new request arrives, you will check whether you have token available or not. If it is available, then you just allow it. Otherwise, you just say no and reject it. Okay. Now distributed challenges. What challenges you will come, as we said that the functional requirement should work in a distributed environment. What distributed challenges you will see? So the first one is multiple instances. Okay, you have 3 gateways. Let's say gateway 1, 2, 3. All must share same counter, right? Otherwise, if everybody share will have different counters, or let's say local counter in case of eventual consistency. Okay, so then the result will be different, right? So all must share the same counter. Solution, what is the solution for this? Centralized Redis. Okay, and then atomic operation. So atomic operation means so the operation, if all three requests, let's say 3 requests is coming at the same time, the user should not, means it should not behave like everybody individually get the current value. Okay, so it should be updated. Now problem second is race condition. So this is the race condition, 2 requests same time. So this one is the race condition, and multiple instances, this one was the other one. Okay, now in race condition, 2 requests same time, so Redis atomic command and Lua script. So what is Lua script? Lua script is code executed atomically on Redis server, okay, to perform multiple operations as one single steps. So let's say two requests is coming, so these are multiple operations, but you will perform it as a single step. So it will not you will not get the race condition. Third one is latency. So calling Redis every request, okay, so means it will take some time. So you should have local cache, or send in a batching. Okay, send means group multiple requests and then send them as a one batch. And then async refiller. So asynchronously you just update that. So if you see production architecture, this is the production architecture. Okay, so client, so the request will go to CDN, and from CDN it will go to API gateway, then rate limiter, then it will store value in a Redis cluster, and then to service if it will allow, then in that case. Okay, now rate limiter with AI. Let's talk about AI part now. So AI, traditional rate limiter is static. AI based rate limiter are dynamic and adaptive. Okay, so how? Let's see use cases. First one is adaptive rate limiter. What is adaptive rate limiter? So let's say, see, in traditional way we were just saying that allow 100 requests per minute, which was fixed, but now here AI will adjust it according to his algorithm. So like for normal user it will be 100, and for suspicious user it will be 220. For premium user it will be 500. Okay, so AI will handle it and adjust. Now bot detection. So AI detects abnormal traffic, repeated pattern, and scrapping. So what is scrapping? Automatically extracting data from website using program instead of human. Okay, so they run program on your website and then they scrap data, like for example product detail or something, different things. Okay, so example, user sending 1000 requests per second. So it means an IP rotation and same header. If these things this thing AI see that okay, one user he is sending 1000 requests per minute, why he is sending, okay, that is suspicious. Then IP rotation, and IP is getting rotated, means from different IP he is getting, and then but header is same. So then he will classify, AI classify as bot, like this request is coming from bot, okay, and throttle heavily. Now burst prediction. So burst prediction also he can do, like AI predict traffic spike, okay, if there is a sale event or cricket match or product launch, okay. So in that case definitely the traffic will spike. So in that case he will just increase rate limit before spike, because he knows that okay, that traffic is coming from correct source, okay. So that is that's expected. Now smart abuse detection. So what is a smart abuse detection? In a traditional way, so we were just checking IP address, okay, but here he will see the behavior based device fingerprint and request pattern, okay. So this is more accurate, AI is more accurate. AI based architecture. So this one will be, see, this part is similar to traditional one, okay, means client, then gateway, rate limiter, rate, okay, after that Redis cluster, and then service. But here in AI, what is extra? So extra is logs, okay, he will add all the data in the log, and then feature extractor, he will extract feature from that, and then ML model will run, and then rate decision will come, like this is the risk factor and all. So this ML pipeline we will discuss here in this video, okay. Features used by AI. So features used by AI is let's say request rate, okay. It will, so you will have a raw data. Let's say raw data is something like user is hitting 1000 requests per second, okay. So what data it will extract from that raw data? So first one is request rate, okay. So in 1 minute, 1 second, how many requests coming. IP entropy. So what is that? IP entropy. Entropy is uncertainty, okay. So he will check, are requests coming from few IPs or thousands of different IPs, different ones, okay. So IP entropy also he will check. Then user history he will check, error rate, geolocation, device type, okay. So for example, if the so all these data features he will store in a feature store, and then AI model will run his algorithm there, okay, and then will the result will come, like the risk score is 0.87. So if 0.87 is coming, then he will assume that this is high risk, and he will stricter rate limit, okay. So he will apply strict rule on that. So for example, user starts sending request, AI detects abnormal pattern, risk score is high, so rate limit initially it was 100, now it will change to 10, okay. He is more strict on that. Redis also he will change it, and then this is how then he can access the service. So this is how he will control the traffic. Now AI data pipeline. So this is what we were discussing, and this one you will use in every system design questions if you're using AI there, okay. So what is the pipeline? See, if you see, so you will get the raw data. From raw data it will convert to features, okay, and then from feature it will convert it, so it will send that feature to train model. So model will automatically train, okay, with that feature data, and then he will use that result in the real time, okay. And for future result also he will use this data, so store it. So the first one is feature extraction, okay. So what is feature extraction? Convert raw data into useful signals. So for example, if raw data is something like this, user clicked 10 times in 5 seconds, okay, this is raw data, and then he will have this IP address, this is the location, and time is 2 AM in the night, okay. So what AI will convert from this data, okay, the feature would be clicks per second. What is that? 2, because if 10 times in 5 seconds, so in 1 second 2 clicks, okay. And this is 2 AM means it is night time, okay. Is night? True. Then location risk is score for Mumbai it is medium, okay. So then he will convert all this feature with this raw data, okay. So these are called features. Now what he will do with this feature? He will store this feature. Where it will store? A centralized place to store and reuse feature. that is called the feature store. Okay, why needed? So instead of recomputing again and again, okay, like in dynamic programming we store data, okay, so that we don't need to recompute it. So that's why that is why save feature once and use everywhere, training and real time. Okay, now for example, feature store contains, like for example, you have a user 123 and his average click rate was 1.2, okay, and last login time was yesterday and fraud score was 0.3. So now this data and this data he will use in the future, and which tools he will use for the feature store. So Feast is there, and then Amazon SageMaker is there, okay, to store the feature. Now the third one is ML training. So it means that teach the model using historical data. Okay, so you will have a machine learning model, and you can have a different version also. Okay, so we will have one table for this machine learning model versions, so that you can change version as well, and there you would have the one accuracy field, so you can store the accuracy also in that table, so that you will come to know, okay, version v1 model has this much accuracy, then v2 the accuracy increased, something like that. So ML training, teach the model using historical data. Okay, you give features to this model. Okay, click rate, IP behavior, label, fraud or not fraud, this data you gave him, and then model learn patterns, like if it is high click and if it is night time, it means it is risky. So for future request he will use this directly. Now output is a trained model, rules plus weights. Real-time inference. What is real-time inference? This is the fourth step of ML pipeline. So using the trained model to make live decisions. So how? See, new request came, like user clicks 20 times in 2 seconds. Okay, so extract feature, send to model. Model says fraud probability was 0.9. So now system action, he will just block the request or trigger captcha and apply a strict rate limit. So this one, whatever action he has taken, is the real-time inference. And what all tools you use? So TensorFlow you use for that, TensorFlow serving, and then AWS Lambda you can use for real-time inference. Now so full flow, if you talk, okay, if we summarize this, then you can say that user request comes, okay, then extract feature like click rate or IP etc, fetch a store feature, send to ML model predict, okay, he will predict whether it is a fraud or safe or hot URL, and then system takes the action. So this is the diagram. So request you will log the raw data first, and then you will extract feature, okay, you will store that feature in a feature store, and then you send this for the ML training, okay, model will train with this data, and then he will take some real-time action, and dynamic rate limiting, then he will apply dynamic rate limiting. Feature store example, Feast and Hops work. So this is the comparison you can do with this. Trade-off. So what is the trade-off here? Without AI, your system was simple, predictable, low latency, and easy to debug. Okay, but when you add AI, then it became adaptive, okay, better abuse prediction, complex, and require model infra. So there it is complex, but that's okay. So you can say that what will be your take here, that you can say that I would start with token bucket based rate limiting algorithm using Redis for strong consistency. At scale, I would augment it with AI based adaptive limits that dynamically adjust quotas based on the user behavior, traffic pattern, and abuse detection, while keeping deterministic fallback for reliability. So that is what we concluded. Now if we check the low level design, see, in low level design we will use this is without AI right now, okay, we will use 8 to 9 classes here. Okay, let's discuss about that. So core components will be first one, you will have a rate limiter service. Okay, so in a rate limiter service, what is his work? He should either he will allow the request or not allow the request. Okay, so he will have only one method, which will be allow request, which will take input request context. Okay, your request will be here, and second, he will respond, he will send output in the form of rate limit response. Okay, so first class will be rate limiter service. Okay, second will be request context, and third will be rate limit response. So now let's see what is there. So in request context, okay, what all input you can provide to user. So first one is user ID, then his IP address, API key, endpoint, which API he is trying to hit, like /login or /search, and then tenant ID. So I explained that tenant is like company, organization, and user is the individual user. So then you will have another one, rate limit rule. Okay, the rate limit rule means you can have different rule, correct, that 100 requests per second user can send. If you have a rule on the basis of IP address, then it would be different, right? So like that, API or tenant. So for example, it will have a rule ID, then key type. Key type will be like whether it is a user and tenancy. For organization, the rate limit will be different, right? 1000 requests per second. For individual user, it would be different, like 100 requests per second, something like that. So key type will be whether you are applying this algorithm on user or IP address or API or tenant. Okay, so that is key type. Key value will be, it's a value, and then endpoint, then limit, how much limit you want, window size, and then burst limit. Okay, so these all things you require. Now algorithm type, you will have another one where you will just add so you have 5 to 6 algorithms, right? So token bucket or sliding window, you just give that value there. And then rate limit response, what we just talked. So in rate limit response, either he will send, yeah, you can allow the request, or he's not allowing the request, that one should come. And then also he should give me the remaining request. Okay, means how many times I can again hit the server. Okay, and then retry after seconds, means try after 30 seconds, that also you can give. Now we will use here strategy pattern. As I mentioned you earlier that for each algorithm you will create different classes, right? And then you will use that classes according to your requirement. So we will use here strategy pattern. Okay, so it will support multiple algorithms. So for example, in rate limiter strategy class, okay, you will have this allow method, and what this allow method will take one key, and second is rate limiter rule. So we have seen that in rate limiter rule we have an algorithm type, and there we have discussed the algorithm also, right? Means mentioned algorithm. So from there it will take that which class needs to be called. So and then again it will give the response in rate limit response time only. So here you will let's say if you can implement these multiple classes, and you can implement that interface rate limit strategy. So this one was this interface. Okay, so for example, token bucket strategy, if you take, so at the end you are storing your value in a Redis only. Okay, so you created one Redis client object, and then in allow method you will override that allow method, and then key would be same, and then rate limit rule you will pass this object, and then on Redis you will run this Lua script, because for the atomic operation, as we mentioned. Okay, so Redis dot execute Lua, and then you will have one script there, and key, and then rule. Okay, now here you will use the factory pattern also. So rate limiter factory. So factory, see, you will create one map of type, algorithm type, and rate limiter strategy. Okay, so you can have multiple strategies like token bucket, sliding window, fixed window. Okay, and then it's a key, algorithm type. So you just add that in a rate limiter factory constructor. Okay, in this map you will populate this map with these values, let's say, and then when someone will ask get a strategy, and then he will give the algorithm type. So from this value he will just return that algorithm type. Okay, now this is the main flow. So main flow, you will have rate limiter service class. Okay, sorry, rate limiter service implementation class, which will implement rate limit service. Okay, which was having only one method, which was allow request. And so here you will have a rule repo first. Okay, from rule repository you will search, you will get the rule, and then from that rule you will extract the information and then pass it to factory. So see here, allow request, what it will do, it will take the request context object, and then return rate limiter response. First he will call rule repository and get the rule. Okay, from that rule he will build one key. Now he will send that key. Okay, before that he will get the strategy also. Okay, from factory, which strategy we are using, and then from that strategy you just call that dot allow method, okay, and you will pass this key and rule in that. So your key, how it will look like, see, it will be something like this: rate limit and then endpoint and then user ID, something like this, okay. So this was the low level design for the rate limiter. Now let's here one more thing, Redis interaction, okay, atomic via Lua. So you have multiple operations there, like increment, expire, token refill, okay. So Lua, what that script ensure on Redis server, no race condition and atomic updates. That's why we are using Lua. Optimization. So if you wanted to optimize this all thing, what you can do, you can create one local cache, let's say caffeine, you will use for that. So cache rule will be TTL is 10 seconds and reduce. So this one will definitely reduce the DB calls, async matrix, send logs to Kafka, and fail open strategy, okay. So if Redis is down, then return just allow the request if Redis is down, instead of blocking the system. Now let's talk about database design, okay. So for the traditional one, so we are still not reached to AI part, okay, but all these things are very important. So you will have 2 DBs here. We will use 2 DBs here, okay. So one is config DB and second is runtime store. So in config DB for the persistent, okay, things, and then for runtime store we will use Redis. So like in config DB, if we talk, like we are using, let's say, SQL here. So first table will be rate limit rules. So what it will have, all your rule information would be there, okay, like ID, key type, okay, per user, per IP, per API, tenant, key value, it's a value, endpoint, okay, limit count, window size, burst limit, then algorithm, like it is token bucket or different one, is active, okay. So you can deactivate also a rule for some time, created at and updated at. Then you will have a tenant limit also. So tenant limit is particular organization. So tenant ID will be there. Then plan type, okay, you will sell different kinds of plan to the organization, like free plan for the trial and premium plan also. Default limit you can set for them, okay. Whitelist, blacklist, I told you, okay. For the client, your authentic client, you will add that in a whitelist, okay, and blacklist for the spam or someone. So you will have one table there, ID, type, okay, then key type, whether the rule type was IP or user, it's a value, it's a reason, okay, why you have put it that in a either whitelist or blacklist, and then created at. Now Redis, okay, so we use 2 DBs here, one is SQL and second is Redis. So now let's talk about Redis, which is runtime store. So in Redis, this is the most important DB for rate limiter, okay. Token bucket model. So here let's say if you are using token bucket, so there you will have key and value, okay, and then tokens you will mention there, and last refill timestamp you will mention there. Now if it is sliding window, so in sliding window again key and value, and then different timestamps, okay, because in sliding window we just update the we just keep track of this timestamp. Now if it is out of range, we will remove it. Fixed window model, so key, value, count and TTL, okay. Now AI based LLD components. Let's jump onto the AI part. So here again you will have different classes, okay. Let's say the first class is AI enhanced. Here you have only 4 to 5 classes, okay. So AI enhanced rate limiter class service. So definitely it will implement this rate limiter service only, okay, that interface. So here whatever AI required, all the fields we will mention here. So for example, rule repository you will use, right, and this is the class, by the way, not the table. So first rule repository is required because you will fetch the rule. Then feature service is required because here we extract from raw data, we extract feature and we store that in a feature store, right. So you would require feature service. Then you will have ML inference client, okay, because ML model also will train this data. Dynamic rate limiter, because now here we are not using a static rate limiter. Machine learning algorithm will check on runtime and change the rate limiting count, okay, value. Then rate limiter factory, So this is allow request, your method, which will take request context, which is same. It will send rate limit response, which is also same. Okay, so first it will fetch the rule from rule repository. Okay, then it will extract feature from that rule, and then he will call ML model on that feature. Okay, and then some result will come. Then he will, according to this result, okay, according to this result, he will adjust the dynamic limit rule, and then he will build a key, and then using strategy, okay, he will fetch that strategy from factory, and then using that strategy you call the allow method and pass the key and dynamic rule. We are doing the same thing, it's just the ML is giving us the value. Okay, now feature extractor layer. So feature service, what it is doing, so in feature service you will have a feature store client. Okay, because you need to store this feature somewhere, so that's why we will call this feature store client object. Okay, we have defined that. Then it will have the extract layer. So now the extract method, what this extract method will take, so request context as a input parameter, and then feature vector as a output, because you need to store this feature, right, in a vector DB. So that's why feature vector type of output. So first you will create the feature vector object. Okay, and then you will get the what is the request rate, what is the IP entropy, what is the time of day. Okay, so whatever data he has predefined, he will extract it from the raw data, and user history also, and then return that that feature vector. Okay, after that you will store this feature vector in the it's a vector DB in feature store, sorry. And then what is feature vector, so it will have the request rate, IP entropy, error rate, is night, user reputation score. Okay, so all these fields which AI will use, metrics which AI will use. Now ML inference client. So ML inference client means it will predict the data and then take action on in real time. So it will have the predict method which will take feature vector. Okay, and then ML result, he will respond. So he will call the ML service. Okay, either it is REST or gRPC, and then return that whatever is the result. So ML result, the structure will be something like this. It will have the risk score. Okay, 0 is safe, 1 is risky, and category, whether he is a normal user or a bot or a suspicious user. Now dynamic limit calculator. So dynamic limit calculator, he will adjust the rate limit, right, from static to this dynamic one. So he will take the rate limit rule and your ML result. Okay, whatever result came from ML, he will take that. Then he will create a new rule. Okay, just clone the existing one. Then he will check if the risk score is greater than 0.8, means it is very risky, right? So then he will become very strict, and whatever was the base limit earlier, he will divide it by 5. So you just you can give any number here as compared to your means according to your business logic. Then if his risk score is greater than 0.5, then divide it by 2. Okay, otherwise whatever is base limit will be your limit, right? Then AI database design. So that was the LLD, and now let's talk about database we will use for the AI. Okay, so there will be few changes, like feature store you will use. So in feature store, user feature, okay, you will have user ID, average request, error rate, last active, reputation, IP entropy. So these fields could be anything according to AI requirement. Second is request log, where he will training the data. So request log will have the ID, user ID, okay, IP, endpoint, request count, timestamp, ease block, label. Then model he will have. So model, I told you that we will maintain different model versions. Okay, so model ID, version, accuracy, and created. So in future, if you need to use different model, just add entry here, right, and start using that model. When you add AI to your URL shortener, you will have multiple models. Model will change over time because today new model is coming, tomorrow another model will come, right? So it should be flexible for that. You need to track, monitor, and control them. Okay, so real-time flow, what it would be: request arrive, extract real-time historical feature, call ML model for risk scoring, adjust rate limit dynamically, apply rate limit using Redis, and log request for the future training. So this is the final thing, okay, that I would extend the traditional Redis-based rate limiter with AI layer that dynamically adjusts limits based on the user behavior. The system extracts real-time and historical feature, calls an ML model to compute the risk score, and uses that to modify rate limit before applying token bucket or sliding window algorithm. I would keep deterministic fallback to ensure reliability and low latency. So that's it.